Welcome to ReLU Radio, the podcast where we unpack the latest and greatest in machine learning research. I'm your host, Adam, and today we're diving into a fascinating paper titled PaliGemma, a versatile 3B VLM for transfer, from researchers at Google DeepMind. Joining me to break it all down is my co-host, Eliza. Welcome, Eliza.
Thanks, Adam. I'm excited to discuss this paper. It's all about a new vision language model called PaliGemma that packs a lot of power into a relatively small package.
That's right. Before we dive in, can you give our listeners a quick overview of what a vision language model is?
Sure thing. A vision language model, or VLM, is a type of AI that can understand and process both images and text. It's like having a really smart assistant that can look at a picture and describe what it sees, or answer questions about the image.
Great explanation. So what makes PaliGemma special compared to other VLMs out there?
Well, the key thing is that PaliGemma is designed to be versatile and transfer well to a wide range of tasks. It's only 3 billion parameters, which is pretty small by today's standards, but it can match or even outperform much larger models on many benchmarks.
Interesting. Let's start with the basics. What's the architecture of PaliGemma like?
PaliGemma combines two main components. For the vision part, it uses a SIG-LIP image encoder, which is a type of vision transformer. For the language part, it uses the Gemma 2B language model. These are connected by a simple linear projection layer.
And how does it process inputs?
It takes in one or more images, along with a text prompt or question. Then it generates a text output auto-regressively. That means it predicts one token at a time. This simple image plus text in, text out setup is flexible enough to handle a wide variety of tasks.
Like what kind of tasks?
Oh, all sorts! Image classification, captioning, visual question answering, even more complex things like object detection and segmentation. The researchers say you can convert almost any task into this format with the right prompt engineering.
How does PaliGemma fit into the broader landscape of vision language models?
Well, it's part of the evolution we've seen in VLMs over the past few years. We started with models like CLIP that were great at classification and retrieval. Then we got more unified models that could do captioning and question answering. Now we're seeing models that can handle an even wider range of tasks in a unified way.
And where does PaliGemma fit in that progression?
PaliGemma is interesting because it's pushing in the direction of smaller, more efficient models that can still match the performance of much larger ones. It's also designed as a base model for fine-tuning, rather than trying to be a one-size-fits-all solution out of the box.
Let's dig into the details of how PaliGemma is built and trained. Can you walk us through the architecture?
Sure thing. As I mentioned earlier, PaliGemma has two main parts, the vision encoder and the language model. The vision encoder is a SIG-LIP model, specifically the VT so 400 meters variant. This was pre-trained on a huge dataset of image-text pairs using a contrastive learning approach.
And what about the language model side?
That's where Gemma 2B comes in. It's a decoder-only transformer model, similar to GPT, but smaller. The researchers chose it because it strikes a good balance between size and performance.
How do these two parts work together?
They're connected by a simple linear projection layer. This takes the output of the vision encoder and maps it into the same dimension as the language model's token embeddings. They experimented with more complex connectors like MLPs, but found the linear layer worked just as well.
Interesting. And how does the model process inputs?
It's pretty clever. The image gets turned into a sequence of tokens by the vision encoder. Then you have the text input, which might be a caption, a question, or a task description. These get tokenized and embedded. The model concatenates all of these together, with some special tokens to mark the boundaries.
And then it generates the output text?
Exactly. It uses what they call a prefix-LM strategy. The image and input text tokens can all attend to each other freely. But when generating the output, it uses the usual autoregressive masking, where each token can only see the ones that came before it.
Now, Training a model like this is no small feat. Can you break down the training process for us?
Absolutely. The training happens in several stages. First, there's what they call Stage 0, which is really just using the pre-trained SIG, LIP, and Gemma models as starting points.
Smart. No need to reinvent the wheel.
Exactly. Then comes Stage 1, which is the main multimodal pre-training. This is where they combine the vision and language models and train them together on a mixture of vision-language tasks.
What kind of tasks are we talking about?
Oh, all sorts. Captioning in multiple languages, visual question answering, object detection, even OCR. They use a really diverse mix to try to teach the model a broad range of skills.
And how long does this training take?
It's pretty extensive. They train on 1 billion examples, which takes about 3 days on some serious hardware. We're talking 256 TPU V5E chips.
Wow, that's some serious compute power. What comes after Stage 1?
Then there's Stage 2, which is all about increasing the resolution. They start with 224 by 224 pixel images in Stage 1, but then do some additional training at 448 by 448 and even 896 by 896.
Why is that important?
Higher resolution is crucial for tasks like reading small text or detecting small objects. But training at high resolutions from scratch would be too expensive, so this two-stage approach is a clever compromise.
Makes sense. Is that the end of training?
Not quite. The final stage is Stage 3, which is where they fine-tune the model for specific downstream tasks. This is where PaliGemma really shines. It's designed to transfer well to a wide range of tasks with relatively little additional training.
All right, so after all that training, how does PaliGemma actually perform?
In a word, impressively. They evaluated it on over 30 different benchmarks, covering everything from image captioning to visual question answering to object detection.
And how did it stack up against other models?
That's the really exciting part. Despite being much smaller, remember, it's only 3 billion parameters. PaliGemma matches or even beats the performance of much larger models on many tasks. We're talking models that are 10 or even 100 times larger.
Can you give us some specific examples?
Sure. On the CO image captioning benchmark, PaliGemma achieves a CIDR score of 144.6, which is right up there with state-of-the-art models. On VQA-V2, a popular visual question answering dataset, it gets 85.6% accuracy, which is again competitive with much larger models.
That's impressive. Any areas where it particularly shines?
One standout is its performance on tasks that require high resolution, like document visual question answering. On the DOC-VQA benchmark, it achieves an ANLS score of 84.8, which is a significant improvement over previous models.
ANLS? Can you unpack that acronym for us?
Oh, sorry. ANLS stands for Average Normalized Levenshtein Similarity. It's a metric used for tasks where the answer might be a long string, like when you're asking a question about text in an image. It measures how similar the model's answer is to the correct answer, accounting for things like small typos.
Got it. Thanks for clarifying. Any other areas where PaliGemma stands out?
Another interesting one is its performance on the MMVP benchmark, which tests for hard visual reasoning. PaliGemma achieves 47.3% accuracy, which doesn't sound great until you realize that other models, including GPT-4V, are below 40%.
Now, one thing I always appreciate in ML papers is a good ablation study. Did the researchers do any experiments to tease apart what factors are really important for PaliGemma's performance?
Oh, absolutely. They did a whole series of ablation studies. One of the most interesting was looking at the impact of pre-training duration.
And what did they find?
Well, unsurprisingly, longer pre-training generally leads to better performance. But what's interesting is that even with just 10% of the full pre-training duration, so 100 million examples instead of 1 billion, the model still performs quite well. This suggests that you could potentially train a pretty good model with much less compute.
That's good news for researchers without access to hundreds of TPUs. What other factors did they look at?
They did a really thorough investigation of the training setup. For example, they looked at different ways of masking the inputs during training, different learning objectives, and whether to freeze certain parts of the model during training.
And what were some of the key findings?
One interesting result was about freezing model components. The common wisdom has been to keep the vision encoder frozen during multimodal training, but they found that it's actually better to fine-tune everything end to end.
Interesting. Any other surprising results?
Another cool one was about image resolution. They found that increasing resolution helps in two ways. You get more information from the higher res image, but you also increase the model's capacity because you're processing more tokens. And these two effects contribute about equally to the performance boost.
Fascinating. It sounds like they really dug into the nitty-gritty details of what makes these models tick.
Absolutely. They even looked at things like how to initialize new tokens they added to the vocabulary, and whether you really need a separate checkpoint for each resolution, or if you can get away with some clever tricks at inference time.
Now, one of the big selling points of PaliGemma is its ability to transfer well to new tasks. Can you tell us more about how they evaluated this?
Sure thing. They looked at transferability from a few different angles. First, they checked the repeatability of their results. Basically, how consistent the performance is if you retrain or transfer multiple times.
And what did they find?
The results were quite stable. For most tasks, the standard deviation of performance across multiple runs was less than 0.5 percentage points. This is good news because it means the model's performance is reliable and not just a lucky fluke.
That's reassuring. What else did they look at?
They also investigated how sensitive the transfer process is to hyperparameters. This is important because in the real world, you don't always have time to do extensive hyperparameter tuning for every new task.
And how did PaliGemma fare in that respect?
Pretty well. They found that a simple, uniform set of hyperparameters worked quite well across a wide range of tasks. For most tasks, using these default settings resulted in performance within 2.5% of what you'd get with careful per-task tuning.
That's impressive. It sounds like PaliGemma is pretty robust and easy to work with.
Exactly. And there's one more aspect of transferability they looked at, which I find particularly interesting.
Oh, what's that?
They investigated how well PaliGemma can transfer to new tasks with limited examples. This is crucial for real-world applications where you might not have huge labeled datasets for every task you want to tackle.
And how did it do?
The results were quite encouraging. For many tasks, PaliGemma could achieve performance within 10% of its full data score using only 4,000 examples. And even with just 256 examples, it often got within 20% of the full data performance.
Wow, that's impressive. It sounds like PaliGemma could be really useful for quickly prototyping new applications.
Absolutely. The researchers even suggest that in many cases, you might be able to get usable results with as few as 64 examples. That's a game changer for domains where labeled data is scarce or expensive to obtain.
Now, before we wrap up, I always like to ask about any interesting tidbits or unexpected findings that came up during the research. Anything stand out to you?
Oh, there are quite a few actually. One that I found particularly interesting was about image pre-processing for segmentation tasks.
Oh, what did they discover?
Well, the conventional wisdom has been that you need to do careful image augmentations and preserve aspect ratios for tasks like object segmentation. But they found that simply resizing images to a square actually worked just as well.
That's surprising. Any other unexpected findings?
Another interesting one was about counting. They found that existing benchmarks for evaluating counting ability in VLMs had some issues, so they actually introduced a new dataset called CountBenchQA.
What makes this new dataset special?
It's designed to be more challenging and representative of real-world counting tasks. It has a more balanced distribution of counts and higher quality images and annotations.
Interesting. Sounds like they really went above and beyond in their evaluation. Any other cool discoveries?
Oh, here's a fun one. They found that PaliGemma generalizes surprisingly well to 3D renders, even though it was never explicitly trained on that kind of data.
Wow, that's impressive. It really speaks to the model's ability to understand visual concepts in a general way.
Exactly. And there's one more thing I think is worth mentioning. They found that for tasks like captioning specific parts of an image, you can get equally good results by either including bounding box coordinates in the text prompt or by actually drawing a box on the image itself.
That's a neat finding. It suggests the model is pretty flexible in how it can receive information about what to focus on in an image. Well, Eliza, we've covered a lot of ground today. As we wrap up, what do you think are the key takeaways from this research?
I think there are a few big ones, Adam. First, PaliGemma shows that you can build a really capable vision language model with relatively few parameters. This 3 billion parameter model is competitive with models 10 or even 100 times larger on many tasks.
That's pretty impressive. What else stands out to you?
Another key point is the importance of transfer learning. PaliGemma is designed from the ground up to be a versatile base model that can be quickly adapted to new tasks. And the results really bear that out. It transfers well to a wide range of tasks, often with very little task-specific training data.
That could be a game changer for researchers and developers working on new vision language applications.
Absolutely. And I think the third big takeaway is the importance of careful, systematic research. The ablation studies and detailed analyses in this paper really help us understand what factors are important for building effective vision language models.
Great points, Eliza. Any final thoughts on the implications of this research?
I think this work opens up some exciting possibilities. By making capable vision language models more accessible, both in terms of compute requirements and ease of adaptation, it could really accelerate progress in this field. We might see a lot more innovative applications of VLMs in the near future.
Well, there you have it, folks. A deep dive into PaliGemma, a small but mighty vision language model that's pushing the boundaries of what's possible in AI. Thanks for joining us on this episode of ReLU Radio. And a big thank you to Eliza for breaking it all down for us.
It's been a pleasure, Adam. Can't wait to see what exciting new AI research we'll be discussing next time.
Me too. Until then, keep learning, keep experimenting, and keep pushing the boundaries of what's possible with machine learning. This is Adam, signing off from ReLU Radio.